Hello all. Today we will be beginning with analysis and design of our steel structure in ETABS. In this new YouTube playlist series, in our previous video we looked at the section designer in ETABS. Section designer is one of the unique features in ETABS that helps you to model some very different cross sections that you may want to use while building your structure. And those cross sections which are not available in your ETABS template, cross section templates, you can draw and model those cross sections in the section designer. So in today's lecture we will begin with the modeling of our structure in ETABS, and we will look at a 3-story steel structure which is covered with a roof truss at the top. So ground floor, first floor and second floor we will have 3 stories. And in today's lecture, we will only look at the defined portion in ETABS. We will see how to define materials, section properties, and then load patterns. So before beginning with ETABS, first let me go to my AutoCAD architectural plan here. This is one very simple plan of a building that we will be modeling in ETABS. You can see here there are 3 floor diagrams: ground floor, first floor, and second floor. All of these 3 floors have the identical spacing arrangement and identical plans for all of these 3 floors. You can see here we have 3 office rooms here. One is larger compared to the other 2, and we have a staircase at the very middle of our architectural plan. So the center to center distance between the columns in Y direction is 5.27 meter, and then there are 1, 2, 3, 4, 5, 6 grids in the other direction, and these are the distances between these grids, and all of these are center to center spacing. So we have these 3 identical floor plans for all of our floors, and then at the top we have this roof truss. So we will model this roof truss also while modeling our structure. So I will share a PDF of this drawing and I will post it on our Facebook page, Inquisitive Engineer. And before proceeding further, I would also like to request you to subscribe to our channel and also like our Facebook page. We have the same name for both YouTube channel and Facebook page, Inquisitive Engineer. And in these 2 or 3 days before, I have posted some very useful links regarding which is somewhat related to the design of steel structures. I have talked about I-beams. Not I have talked about, but I have shared some YouTube links and other links on our Facebook page. So also do like and subscribe to our Facebook page for more information and for the upcoming videos on our YouTube channel. So this is our architectural plan. First, let's see a short presentation here. The designer has more control over the shape of reinforced cement concrete elements, because our reinforced element cross sections, whether it be column, beam or slab, these are cast in situ, or these are cast in our site directly. So we have more control over the shape of reinforced concrete elements because we make them from scratch. We assemble all the required materials including cement, fine and coarse aggregates, and any water admixture if necessary, and then we will cast those elements into concrete and cast the concrete elements into shape in our site itself. In contrast, if you want to build a steel structure, we are compelled to use some standard rolled sections. We have some very typical standard rolled sections. I will come to that in our upcoming slides also. For example, I-beam, our C channels, our T elements, our pipes, tubes, and other standard rolled sections. So these are the standard sections that a designer normally uses. And if you want to see the dimensions for these rolled sections, then you can download and look at this Indian code IS 808. This code is related with the dimensions for hot rolled steel beam, column, channel, and angle sections. And for steel tubes, you can download and read this IS 1161 code. So these 2 codes are related with the dimensions of these structural elements. So if a designer wants to use any other different element as compared to these standard ruled sections, then you have to order those elements. So they can be prepared, but they have to be specially manufactured, those non-standard sections. So what care should a designer have in his mind? What care should he take when designing these steel elements? You do not have the control over the shape of the cross-sectional elements in contrast with these reinforced concrete structures. You have to use some standard sections while designing steel elements. So what points should you take care about? First, you have to select a section which is readily available in the local market. Always be careful that whatever section you are going to use for a particular place or for a particular country when you are designing, you have to be aware of the market situation. You have to be sure that those elements are readily available in the market. If you design your steel structure with very unusual elements or those non-standard elements, then they may not be available in the market. In that case, you may have to redesign again, which will waste your time and which will waste your money also. So you have to always make sure that those steel sections are available in your local market. If it is a very big project, then in that big project, there may be some way to import other structural elements from foreign countries also. But for residential buildings and other small buildings, you have to make sure that this first point is taken care of. Similarly, you have to use such structural elements which are compatible at the joints. That means it should not be difficult to make connections using those various structural elements. For example, you have to make sure that your beam and columns are such that they are readily a connection can be made between those beam and column elements. The elements of steel structures in exposed condition that require frequent maintenance should be easily accessible. Steel structure, if that is used in such exposed conditions, for example, if you have used that steel structure in a bridge or a large tower, then you have to make sure that all the elements are accessible so that they can be subjected to frequent maintenance. Transportation facilities for built-up sections should be explored before designing them. And finally, the structural steel sections should be of a size which can be easily erected without introducing secondary stresses. This means for large structural elements or for tall buildings, you may have to use crane or some other methods while erecting those elements. And that process of erection or that use of crane should not induce any secondary stresses. So it's better not to design for very large cross-sectional sizes, in which case even erection or placing those structural elements becomes very difficult. So our design code is, we will learn about designing of steel structures in this course based on Indian code, and the code that we will be using for designing is the IS 800 code, and that is related with the code of practice for general construction in steel. So what are the advantages of steel as a structural material? First, this is the primary advantage or the main advantage, that is steel members have high strength per unit weight. So what happens is that if you have a high strength per unit weight, that means even a steel member of a small section which has very little self weight is able to resist heavy loads. So that means that high strength of steel results in smaller sections that can be used, for example, and also in buildings. If you are making beam and columns, then that high strength allows us to use fewer columns in buildings. So this high strength to weight ratio is the most important property for the construction of many structures such as long span bridges, tall buildings, and for also buildings on soil with relatively low bearing capacity. This high strength per unit weight is the primary advantage. Similarly, steel being a ductile material does not fail suddenly but gives visible evidence of impending failure by large deflection. So this ductile nature of structural steel means that they yield locally at the point of high stress concentration. There won't be any direct failure of the whole building or whole structure, but they will yield at certain locations at which the stress concentration is very high. That means The ductility of steel is also responsible for relieving the overstressing in certain members by allowing redistribution of stresses due to yielding. That yielding at certain locations gives way to the redistribution of stresses so that there aren't any premature failures. So structural steels are tough. They have both strength and ductility. That means if they are subjected to large deformations during fabrication and erection, they will not fracture. Also, they may be bent, hammered, sheared, or even the bolt holes may be punched in our steel elements without any damage. Being light, steel members can be conveniently handled and transported. One example is the increasing use of the prefabricated steel elements while constructing buildings and different types of truss buildings. It is because of this light nature of steel members so that they can be easily handled and transported. Properly maintained steel structures have a long life. The properties of steel do not change with time. This makes the steel most suitable material for a structure. So addition and alteration can be made easily to steel structures. For example, if you have constructed a simple truss garage at a certain location, and you may have to move from that location at a future point of time, then you can construct that truss garage in such a way that you can dismantle that truss garage at a final time when you are ready to move to another place. You can transport these dismantled elements to another place, and then you can again easily erect those steel elements to make the same garage at another location. So they can be erected at a faster rate, and one final advantage is that steel has the highest scrap value amongst all building materials. Also, there are some disadvantages. Steel elements require frequent maintenance. They need fireproof treatment, thus increasing cost. You know that those steel members, since they are excellent heat conductor, they may even transmit enough heat from a burning section. That means steel elements are subjected to fire vulnerability very much. Not only at one location where there may be fire in our building, but this excellent conducting capacity of steel also may transmit that heat and fire to another location. And finally, fatigue is one of the major drawbacks of steel structure. So these are some advantages and some very few disadvantages of steel structure. So we talked about the rolled steel sections in our first slide. These steel sections are manufactured in rolling mills, so they are called rolled steel section, and these are used as structural member. So these rolled steel sections are named according to their shape. For example, if you see here, this is in the shape of a capital I, so this is our I section. And since this is normally used as a beam, we have called this a beam section here. Similarly, this shape of C is our channel section or C section, and this shape of T is a T section. So many steel sections are readily available in the market and have frequent demand. Such steel sections are known as regular steel sections. Also, standard steel sections that we talked about a little earlier. Some steel sections are rarely used. Such sections are produced on special requisition and are known as special section. For only very big projects, we may want to use special sections. Otherwise, our normal or standard steel sections are sufficient. So ISI Handbook for Structural Engineer gives nominal dimension, weight, and geometrical properties of various rolled structural steel sections. So we have talked about this here: I section, C channel section, T section. Similarly, we have angle section. This angle section may be of equal angle. If the length of two legs, L and L, are same, we call it equal angle. And if these lengths are different, L1 and L2, we call it unequal angle. And also we have bulb angle here. Our steel section also may be a tube section. This is circular in cross section and it is hollow in the middle. Similarly, we may have flats, steel flats. You may notice that we use this steel flats a lot when making some steel staircases. Then we also have this solid, square bar and round bar section. So these are some of our rolled steel section. So These were the example. These are different type of rolled steel section. I have listed the names here: I section, channel, T section, angle, steel bar, steel tubes, steel flats, steel sheets and strips, and steel plates. These are some of our rolled steel section, and all of these are standard sections. So rolled steel I-beam and rolled steel channel section, I will not go through these slides for now. If needed, we will return back to these slides in our future videos. So this was our general introduction to the steel structure, their advantages and disadvantages, some points that you should take care while designing steel structure, and then some standard rolled steel section. Now we will begin with ETABS, and we will begin defining various types, various things, including these materials, section properties, and load patterns in today's video for the analysis and design of our steel structure in ETABS. So I have already opened my ETABS here. I'll go to File and New Model. So one thing that you have to take care is designing a steel section is a little bit more difficult compared to designing a RCC element or RCC structure in ETABS. There are some important things to take care, and we will go through step by step in all of those processes. So there will be many videos in this playlist. We will discuss and we will design and we will upload these videos in our YouTube channel, as many videos as possible, as many videos as are needed. So we will look into the detail of the design of different types of elements, different types of connection or footing individually in a separate video. So as we go through these videos, and if you think something is missing or if you want to learn about something, then do comment under these videos in our YouTube, or you can also send a message to us through our Facebook page. And do not worry, we will go through each design phase or each analysis phase one by one, and if we miss something in the middle, then we will come back to that at the end or in separate video lectures also. So our model initialization form is open. We will use built-in settings with display units. I will select as metric SI, steel section database Indian, steel design code IS 800, and concrete design code. Although we do not need this for now, I will select as IS 456 and then left click on OK. So let me select custom grid spacing and custom story data, and then go to edit grid data. So I will select these display grid data as ordinates, and in the X grid data you can see in our architectural plan that we have 1, 2, 3, 4, 5, 6 grid with different center to center spacing. I have already copied this center to center spacing in one page. I will just look at that and then enter those spacing in our ETABS model. In our Facebook page, I will just make a PDF of this plan and I will post it, and I will also post a link of this architectural plan under our video also. So do check for that. So in the X grid data, we will display grid data as ordinates. A will be 0, B will be 3.325, C will be 5.675, D will be 9.05, E will be 12.425, and then F will be 10.685. So this is our grid spacing in X direction. And in the Y direction, we only have 2 grids, and these are at a distance of 5.27 meters. So I will delete these 3 and 4, and 2 spacing I will keep it as 5.27, and then left click on OK. And now we will edit our story data. So we have base here, and we will take our story to story height as 3.2 meter. So story 1 3.2, story 2 3.2, story 3 also 3.2, and finally story 4. Let's see here that this height of our truss is 1.2 meter, this height of central strut here. So story 4 I will keep as 1.2 meter for our, sorry, I will keep this as 1.4 meter here for our height of truss. Actually our height of truss is 1.2 meter. This 0.2 meter extra is necessary. I will discuss that when drawing our different structural elements at a later phase. So let's left click on OK. So we have defined the grid and story data. Now left click on OK. So here is our story data here. I'll just close this Model Explorer for now, and I will continue with other define options. So after completion of this story data, go to define, and first we will define materials. There are some default materials here. We do not need this. So for now, first we will add material for concrete. We will see why we need material for concrete when we go to design. So go to concrete, Indian and grade EM20, and then left click on OK. Again left click on OK. And for steel structure, our steel sections are made up of mild steel, that is Fe 250 grade. So go to material type and then select steel. So remember, if it were our steel reinforcement, that is our rebar in structural concrete, then we will select this rebar. For structural steel, select this steel option. Standard will be Indian and the grade will be Fe 250. And then left click on OK. Left click on OK. So we have defined these two materials that we need, and I will left click on OK. So after defining material, let's go to defining section properties. Go to define section properties and frame section. So in this definition of section property, first let us define some section properties for our truss elements here, for these elements that form our truss. Okay, consider that we will be using our tube elements, that means round hollow elements for our truss. So our round hollow elements are represented by the letter ISNB. You may know this, ISNB. So let me go to my presentation slide for once, and let me go to this here. You can see that our rolled steel beam sections, that means I section, are also of different types. For example, we have here ISJB. This means Indian Standard Joister Junior Beams. And then again ISLB, Indian Standard Light Beams, Indian Standard Medium Weight Beams, and then Indian Standard Wide Flange Beams, ISWB. So these are our representation of different element type, and this Indian Standard Medium Weight Beams, ISMB, is the one that we will use, and that is mostly available in the market. So when we define for beam section, then we will define these ISMB sections. Here B stands for beam here. Similarly, if it were a C section or a channel section, then we will use this ISMC section. Although we have this same ISJC, ISLC, ISMCP, we will use this medium weight channel sections. The C represents channel, so we will use ISMB section. And in case of the pipe section or our tube section means we have a circular tube of certain thickness and it is hollow inside this tube. This part is hollow. So this means Indian Standard Nominal Board. Nominal Board. So if you have any representation such as ISNB 50M, then this means we are using a steel tube section of 50 mm diameter, and M means this is medium weight section. So this 50 mm diameter tube section also has different thickness of this tube, and for the thickness of middle value, that means if you have this 50 mm diameter tube of 2, 3 and 4 mm thickness. This 3 mm thickness is known as the medium weight. So we will represent that by M. So this is how you represent a steel section. After this ISMB 50 mm or ISMB or ISMC, you may also write the kg per meter or weight per meter length of that steel elements at the end. So this is the way to represent your structural steel section. So for truss elements, we will be using these tube sections. So what I will do is I will import new properties here, and these I will be importing this steel tube section or pipe section. So left click on this pipe section. Okay, here are different pipe sections. You can see ISNB 15H, 15L and 15M. That means of heavy weight, lightweight and medium weight of 15 mm diameter. So what I will do is I will import some properties. I will import this ISNB 40M, ISNB 50M and then ISNB 65M. These three pipe sections of medium weight of 40 mm diameter, 50 mm diameter and 65 mm diameter for our truss sections. And if these are not sufficient, then when we design our structural elements, we will again import some elements of larger diameter and then perform analysis and design. For now, I will only import these three elements and then left click on OK. So these three elements have been added. Let me delete other so that we don't get confused here. Okay, I have deleted other elements and I am only using this ISNB 40M, 50M and 65M. If you want to see the details of this, just select this 50M and then left click on modify show property. Okay, one thing I have forgotten to do is I have forgotten to change the material for these steel elements. So select any one of these steel elements, go to modify show property and change the material to Fe250 and then left click on OK. Again for 50M also do the same thing, change the material to Fe250, left click on OK, and for 65M also the same, Fe250. Let's look here. This 65 mm is the nominal bore. You can see that the outside diameter is, since this outside diameter also includes the thickness, the outside diameter is 76.1 mm and the wall thickness is 3.6 mm. So let's click on OK. Now after this tube section, what I will do is I will import some channel sections here. For that, I will again go to import new properties, select this channel section. Again, I will select this medium weight channel sections, ISMC. So let me select for now ISMC 100, 125, 150, and then 250, and then 300. And let's click on OK. After these channel sections I have imported for our columns. Columns we will design using section designer, and I'll come to that after some time, and also for secondary beams here. So these channel sections are for columns and secondary beams. And for beam sections, we will import some I sections. Go to import new properties. Okay, I have done the same mistake here. What I will do is I will go to this delete multiple properties and I will delete these channel sections for now. I will again go to import new property, select this channel section, change the default material for section to Fe250. If you change the default material here, all these sections that will be imported will have this Fe250 material. So instead of changing one by one from this side here, I will just change this default material for section to Fe250 here. And then I will select this. I will left click control on our keyboard and then select this ISMC 100, 125, 150, 250 and 300 and then left click on OK. So you can see here this dash is coming because we imported once, so it won't matter. So ISMC 300, let's look at the properties of this section. Modify show property. Now the material is already Fe250 here. So you can see that this 300 means that the total depth of our section is 300. If I go to my presentation slide here and then go to here, you can see that this is the depth of your section. Here we have the depth, this is the width. This part is known as the wave and these two are the flanges of our channel section. Similarly, for I section also same, this is the wave and these two are the flanges, and this is the total depth and this is the width of this I section. So the total depth is 300 mm. This depth is 300 mm, hence it is known as ISMC 300. This total width is 90. The flange thickness is 13.6 mm. The thickness of these flanges at the top and bottom is 13.6, and wave thickness is 7.6 mm, and fillet radius we have 0 mm. So let's click and cancel. Now after this we will import our I-beam section. So left click on import new properties again. Select this I-beam. Change the default material as Fe250, and for now I will again import some medium weight beam section. So I will import ISMB 250 here. Click on Ctrl on your keyboard, do not let it go. Again select ISMB 300 and ISMB 350. I'm selecting these range of beam section and channel section because ours is a 3-story building, and once you are used to designing various steel buildings, you will have a certain idea about what size of structural elements are needed. And then left click on OK. So let's see here. We have selected a range of medium weight beam sections, this 250, 300 and 350, and again a range of channel sections, MC 100, 125, 150, 250, 300. So you don't know which section is going to be the most suitable for our structure. What we can do is we can select a list of these sections and then we can ask the software to choose by itself. Instead of designing a model and see if it is passing or failing under various stress checks, unlocking the model again and changing the cross section if your structure is failing, what we can do is we can create a list for beams and we can also create a list for columns, and what we can do is we can ask our software to select the optimal size from those list itself. So for that what I will do is you can go to this import new properties and then go to this auto select list. What auto select list does is that it creates a list of different types of structural elements, and then the software chooses the optimal size from these elements that are added to a certain list. So we have to import these sections again. Instead of importing, what I will do is I will go to this add new property, because if you go to this import new properties, you will have to import from the elements that are added to this library of ETABS. But if you select this add new property, you can select the structural elements that you have already imported here. So left click on add new property and then go to this auto select list. Let's name this list as auto beam, because in this list we are going to add those structural elements from which the software has to select for using as beams. And since this is beams, I will add these 3 ISMB sections to this list. For that, select these 3 elements and then click on add. Now what the software does is it starts our design with this medium section here. Here 250 is the smallest and 350 is the largest in this list, and 300 is the medium section. So if 300 medium section is sufficient, then it will use this section. If it is larger as compared to what we need, it will use this ISMB 250 section and then check for design using this section. However, if this 300 mm is smaller, then it uses this 350 mm section and again checks for the design. So the software will start with designing with the help of this medium section and then go to other sections. And finally click on OK at the bottom. You may not see that OK option in my screen, but you will have to left click on OK. Now similarly, I will add new property again and then left click on this auto select list. This time I'm creating an auto select list for secondary beam. So let's rename this as auto sec beam. And in this list I will add these ISEMC channels, not all, but this 100, 125 and 150. If it is not sufficient, then we will see what will happen at later stage. For now I will select these elements and add to this list auto secondary beam. Now again, our software, once we model any element using this auto secondary beam option, then it will start our design with this ISMC 125 section. If this is very much large, it will go to this ISMC 100 and then again redesign using this section. And if it is less, then it will go to this higher section, ISMC 150, and then again redesign using this section. And then left click on OK. So we have created two auto selection lists for beam and secondary beam. For columns, I will not be using any auto select list here. Here for columns, I will use one section designer. In our previous lecture in this YouTube video playlist series, we have looked at the property or this very useful application section designer that is available in ETABS. I will not repeat again about this section designer. I will directly go to section designer and create a composite beam or built up beam. If you have noticed about the steel structures that is generally built, you can see that those steel structures are built using composite columns, and these composite columns are generally made from two channel sections that are placed this front to front. Generally we use this composite built up column section for columns, and then we use I section for beam. Now you may say, why we don't use this single channel section, or by using a comparatively larger channel section, but why we do not use only this one channel section for column? Because you can see that this channel section is not symmetrical about this y-axis here. So to make our column section symmetrical, we create this built-up section by using two ISEMC section or two channel section placed front to front, or you can also place this channel section back to back in this way. So for now we will use section designer, and since this cross section is not available in ETABS, we only have this single ISEMC section. We will use section designer to create this section, and when we look at the design of columns at our design videos, then we will see how to create these columns and how to join these columns using these batten plates. Let me just go to this Google and see here built up steel column. And you can see in this diagram here, for example, if you look at this diagram here, you can see built up column sections. All of these are built up column sections, and these columns have used I section and these have used channel sections. In this way you can create built up column sections to be used in our structure. So how to create this built up section? What I will do is I will use these two numbers of ISEMC 300 section. ISEMC 300 section to create our built up column. If you remember, we looked at the property of ISEMC 300. You know that the depth of our 300 ISMC 300, this is 300 mm, and the width of these flanges is 90 mm. So what I would like to do now is create a 300 by 250 mm column using this built up section. So this is 300, means we have to make the dimension 250 in this side. Now the dimension of this flange is 90 mm, the dimension of another flange is 90 mm, which we get 180. And to make this 250 mm, we have to keep a gap of 70 mm. because 180 plus 90 plus 90 plus 70 is 250. So we will use another ISMC section here. This means 90 plus 90 is 180, and 180 plus this gap 70 will be 250. So total will be 250. We will create this kind of column. For that, I will go to ISMC 300 and then left click on this, convert to SD section. Let me rename this as 2 ISMC 300. Okay, you can give any name that you like, and then left click on this section designer here. So you can see that this ISMC 300 channel is already given here. So first what I will do is, you can see that the dimension of this column is 90 mm, and currently this is being situated, or this is being placed at the center of this y-axis here. So this gap will be, let me just write here, since the width of our flanges is 90 mm, currently what you can see is that this will be 45 mm and this will be again 45 mm. So what I have to do is, I have to move this center of this, since this is the center, I have to move this center to a little bit to the left to create out this built up section. So what I will do is, I will select this channel section and then right click on it, and then I will change this X center to minus 67.5 mm and then left click on OK. So now you can see here, if you look at this right bottom corner, then you can see that the value of X here is minus 112.5 mm. So this is minus 112.5 mm. If you create another distance at 112.5 mm in this positive x-axis and place our I section here, then you will create this ISMC 300, this will be 300, and this will be 250. So to create another same ISMC channel section in this other side, what I will do is select this section here and then go to edit and then go to replicate. We will use the mirror option and we will mirror this section about our y-axis, that is vertical axis, y-axis. We do not want to delete our selected objects, so do not check this and then left click on OK. So here you have created this 2 ISMC 300 section, and the spacing will be this dimension in the x direction will be 250 mm and the dimension in this y direction will be 300 mm. So this is how you create a built up column section in section designer, and then left click on OK and again left click on OK. So we have created this built up column section. If you are confused with how to create this built up section, rewatch this section designer portion 2 or 3 times, how much it is necessary, and then practice on your own. It is very easy to create this built up column section. So these are all the cross-sectional properties, column section, beam section, that we will be using in our program here. So this much is what we need here, and left click on OK. Now for slab, we will use this deck section. If you go to Google and search for, you may search for example, metal deck sheet, and if you look at these diagrams, you can see that these profile seating are generally used for slab section or as composite slab in our steel structure. So what I will do is, I will make a separate video about how to select these properties or how to select the dimensions for this steel slab deck sheet what are the advantages, how are they installed, why do we use them in a separate video. For now, I will only define the dimensions and properties of this metal deck sheet in this lecture. So I will go to define and then section properties and slab section. Okay, let's rename this slab 1 here. Select slab 1 and then left click on modify show property. Okay, not slab section, sorry. Let's go to define section properties and this deck section. And let's modify this deck 1 property. Let us give the name is deck slab here. The type that we will be using is field section. If you hover onto this I here, you can see the field deck. Our slab material will be M20 because we will use concrete over this slab, since this is our composite slab section, and the deck material will be FE 250. This modeling type is not active here. Now I will have to use this various property data for our deck slab. If you hover onto this here, you can see some different properties and these symbols here, and you can see what these symbols represent. For example, here you can see HS on this side. This HS means shear stud height. Similarly, you can see SR. SR, it is the reeve spacing. Similarly, you can see WRT and WRB. WRT is the top width of the reeve and WRB is the bottom width. Similarly, you have TC and HR. TC is the slab depth and HR is the reeve height. So how you can include these property data here? Different companies manufacture these deck slab, and if you go to these companies website and download brochures or different information, or you may visit these companies by yourself practically also, and they will give you all the required information according to the type of deck slab that you manufacture. So in Nepal, I have seen this deck slab being manufactured by Panchakanya Group. So if you go to Panchakanya website, there are not some exhaustive information available, but there is some information regarding this deck slab. So for now, I will be using some property data randomly based on the information that I have, and we will discuss in a separate video about these metal decking systems. So slab depth, let's use the same 87.5, HR 75, WRT 175, WRB 125, reeve spacing 300, deck shear thickness 1 mm, deck unit weight 0.11, shear stud diameter 19, and shear stud height 150. Shear stud tensile strength 400 megapascal. So for now, I am not going to change any of these default values and let them be as they are. So let's click on OK, and then let's click on OK. So before going further, let's save our model. Save it in your folder of your choice. So I will make a new folder here. I will give the name as Steel Office Building, and then I will save this model. So today's video has become a little longer, so I'm going to stop here. We are still left with defining mass source, load patterns, and load combinations. So we will look at that definition portion in our second video. So we will meet again soon. We will continue with this lecture in our next video also. So see you again. Till then, stay safe. Thank you.